So today I'm going to go and talk a little bit more in detail or depth about some of the things that we did at Netflix using both Trino and Iceberg. Hopefully give some background on how Trino works and what you can expect from it, and then how it's also very complementary to Iceberg as a new table format. So let's just jump right in. The motivating use case that really drove home to me how nice it was to use Trino was this question that came in a few months ago, basically saying, hey, I've got a Spark query and a Trino query, literally the exact same SQL. Spark takes more than an hour to process this, and Trino takes under 5 minutes. Can you just tell me what's going on? And I was really shocked by this because I thought, Spark does a great job in many ways. It has, whole stage code gen, the kind of push down operations that you would expect. Like, I didn't expect for there to be this significant of a difference in runtime, especially when we're talking about a very simple query that is just doing filtering and aggregation, and literally running the exact same query on the exact same data. Now, this was a little weird because we had a million tasks or a million file splits. So this was quite a large query. It didn't surprise me at all that Spark took, 30, 60 minutes, something like that. What I found really surprising was that Trino took 5 minutes to get this done. And so I sort of did some digging, and I want to talk about that today because I'm just really impressed that Trino was able to get this done. So first off, let's start by saying that this is definitely not a benchmark. This is not like us scaling up a Spark cluster and giving it the exact same size or number of nodes, number of cores, amount of memory, anything like that. What this was is a very real world situation where we had a Spark setup that was tuned for ETL workloads. We had a Trino setup that was, essentially used for our ad hoc workloads. And that's, basically where we were. We had two systems set up for very different things. And so we shouldn't necessarily expect them to have the same performance characteristics. But what I would say is that these were tuned very reasonably for getting things done in Spark and a different set of use cases for Trino. And what it drives home is how optimized Trino is for fast results from large scale data warehouses. So let's start by talking about a couple of the things that we know were going on with Spark that either weren't problems in Trino or really make this a different situation. So first of all, we know that the Spark scheduler has a lot of problems. So in the Spark scheduler, as it's trying to figure out where to schedule tasks and has RPC messages coming in and out and saying, okay, you executor number 10, go run this task and get a message back. Oh, that was completed. I need to run another one on that executor. They're just issues. So first of all, Spark was built around the actor model initially, which is a completely isolated, like process one message at a time kind of programming paradigm. And so the scheduler and other things basically used synchronized methods and locked at a very, very coarse level. And this was never really fixed. So in terms of like a lot of really small tasks, Spark doesn't ever do a great job. So that coarse locking is just a serious limitation. The other things that we know might have affected this is tasks are very easy to include lots of state in. So each task in Spark ends up being a closure in Scala that has, potentially a ton of accidentally introduced state that gets serialized, shipped over to an executor, deserialized, and that whole process can take a significantly long time. Now, we're talking on the order of maybe half a second for really large amounts of state, but that half a second per task for every single task really adds up. So this is again in a case where we're trying to run a million tasks. Normally, the course locking doesn't matter. Normally, the task state doesn't really matter, but we're really pushing Spark to the edge here. There's also a lot of confusion, and this is where this was our setup. So we were running Spark in Yarn. We were sharing resources by scaling individual Spark clusters or applications in Yarn up and down. And that whole dynamic allocation thing has some issues as well, where as you're trying to scale up, it's going to do like an exponential scale up. But there are three different things tracking resources at that point. You've got the Spark scheduler with its course locking. You've got Yarn Yarn allocator talking to the Yarn system itself and saying, hey, give me these executors or these containers and shut down these other ones. And then you've got something sitting in the middle between those two things, trying to broker that interaction and say, okay, the scheduler has this many tasks. I should have this many executors. And there are so many RPCs flowing back and forth that you never quite get in a consistent state. So this is not a talk about Spark. I'm just trying to, set the stage for this is not really a fair benchmark, right? But what I think we should take away from this is that all of these problems are sort of fixed out of the box in Trino. So Trino doesn't have this relationship with Yarn because it doesn't really run in a Yarn cluster. Its scheduler and resource manager, worker pool, all of those things are built dramatically differently. So you have one coordinator, all of the workers are connected to that at all times. It's not like you're trying to scale up and scale down, and it goes into a lot of other optimizations. So rather than trying to serialize an entire closure from some Scala application, what it's doing is it breaks up your workload into tasks and then has a well-defined JSON representation for those tasks. So everything is super lightweight. You send it over, and that worker starts working on a task right away. And so that's just one of the things that Trino is doing in this case to take that hour of runtime down to 5 minutes. Workers are already connected, ready to scale up for processing a query. The tasks are lightweight, so the basically task dispatch goes incredibly quickly. And that, I think, was one of the main differences between Spark and Trino in our use case. There are other things that just make Trino, simply really super fast for queries. I'm not the expert here, but I do want to highlight at least two. So first of all, Trino has optimizations like running planning and tasks in parallel. So as soon as a connector starts producing tasks from that job planning phase, Trino is going to start running those tasks on workers, seeing how they execute, maybe scaling up to a larger worker set or not, but we're basically immediately getting feedback. So if you're running a limit query, you get feedback, or you get the first 100 rows almost immediately, well before job planning is even finished. And if you're running a very heavy query, like our 1 million task example, the job planning is not added to the runtime. You're running those things in parallel, and so you're really able to take advantage of shorter wall times thanks to that planning and running the job in parallel. Now, the other thing that Trino does incredibly well is it has its own reader. So Parquet and Orc reads go directly into Trino memory. It's a vectorized read. It's very well optimized, super quick. And so it's really a great read path. And that just goes to make all of those, all of those operations really, really quick. So we have fast planning, that runs in parallel with the tasks. Really quick task dispatch because we're only creating a JSON blob, sending that to a worker, and then the worker is already scaled up and ready to go. Once the worker gets that task, it knows what to do very quickly, and then goes and has a highly optimized read path to get that data into memory and start running your query processing on top of it. And the result is really quite striking. It is a 5-minute query versus an hour. And so I think the takeaway here is that Trino works surprisingly well, like just really impressive, no matter how your data is stored. All of those things, each stage of your query was really well thought out and well designed. But the problem is, I think we're holding Trino back. The problem now becomes that tables themselves are inefficient. Query planning can take 10 or more minutes. That could be aggregating a set of data files from diffs across. So you might have one big checkpoint file of files, and then you need to add 100 diffs to that, maybe do that aggregation in parallel, and then bring that back, filter the set of data files, and then get your tasks out. Or in the case of Hive tables, you might be listing thousands, tens of thousands, hundreds of thousands of partition directories to figure out what data files actually need to be read for your query. That can take an incredibly long time. One of the first things I did at Netflix was parallelize this in Spark, and that was to get the the planning time for a query down to tens of minutes instead of hours. And so the query planning, it's incredibly important to run this in parallel while you're in parallel with your job. So as soon as you get splits, you're actually running those on the Presto cluster. But at the same time, a 10-minute planning time means that you cannot finish the query in under 10 minutes. And so good luck with, fast queries. If our 1 million split example had taken 10 or more minutes to just plan, then it would have taken at least 10 minutes for that query to run. So this is a bottleneck that we need to solve. The next way tables are inefficient is more hidden by Trino than anything else. So Trino is a large cluster sitting there ready to go for any query that comes in. We've already scaled up in most cases, although there is the auto scaling up and down that you can do if needed. But most fast queries just rely on the workers already being there. But that doesn't necessarily mean that queries are efficient. So what we would see is if you're listing and planning too many tasks, then you could even have the number of tasks that are 2 or 3 orders of magnitude more than just the tasks that actually contain data for the query. And the way this works is you might have, you might be looking for a certain user ID and your data is partitioned by hour. Well, maybe that user wasn't active for an hour, but if all you have is the partitioning of the table, you have to read every single file in that hour. And so what we want is a way of pushing down that filter more directly, actually filtering out data files and knowing more about what's in the files in order to avoid having so many tasks. It's not that we can't just scale out and have hundreds of workers or thousands of cores working on this at the same time. It's that we really don't want to do that for efficiency reasons, because that's just taking resources that other queries could be using at the same time. And the other thing that is really terrible about having just way too many tasks for a query is that you're more sensitive to any issues in the backend. So what we found at Netflix was when we were running these queries, we had this problem where S3 would randomly hang. So most of the time you'd go to S3, ask for data, get it back and process in a matter of milliseconds. But what was happening occasionally, and this was like, 1 in 100, 1 in 500, something like that, the query would hang for some reason, right? S3 just wouldn't give us the data back. And what you're supposed to do in that case is try again or cancel or something, but you can just wait. And this was causing a lot of queries to take significantly longer than necessary because 1,000 tasks hits this probably once, whereas 100 or 10 tasks doesn't hit it at all. So it makes queries a lot more sensitive to any backend problem like S3 hanging, just to have more tasks than necessary, even if we can scale out and just chunk through them and get that work done. So these are limitations of the table formats themselves. Query planning time taking a really long time, and just not having the metadata necessary to really filter down to just the data files that actually have data for a query, or are more likely to have data for a query. So that begs the question, and I'm sure everyone knows, since I'm the Iceberg guy, where we're going with this. What if we fixed tables? It seems so novel, doesn't it? Well, that's actually why Iceberg exists, to fix these table problems. The problem, that statement isn't quite true. So Iceberg exists to fix tables at a high level, but I don't think that we can just say fix without relation, without thinking about what are we fixing. So what we really want to think about is that Iceberg exists to fix developers and analysts and data engineers' productivity across the board. So this is broader than just the task issues and job planning issues that we're talking about today. It actually consists of three things. So first of all, data engineers, data analysts can't be productive without reliable transactions. If the mode of operation is I need to overwrite this portion of a table, I'm going to go delete everything and hope that the write succeeds, that's not a recipe for success. So Iceberg fixes transaction semantics and makes things reliable. It also does what we're talking about today, which is unlocks performance. Really gets to the point where we can build more performant systems. So we're not just scaling out queries, we're actually doing only the work needed. And the last thing is fixing usability. This is things like being able to rename a column if you need to, without, I mean, some systems will actually fail and say, hey, you can't rename a column in this format. But most of the time it just allows you to, and then you have a new column with a different name, and you have to coalesce them together or otherwise go back and fix that issue. So there are a lot of rough edges, and this is really where our message of fixing productivity makes more sense. Because if you run a DDL statement and that corrupts your table, that's not usable enough for you to be productive. So Iceberg also fixes those issues, adds in-place evolution and a lot more things. But again, today we're focusing on this middle one, which is to unlock performance bottlenecks. All right. So let's talk a little bit about how Iceberg does that. Iceberg has a few optimizations that I just want to touch on briefly here. First of all, Iceberg is built for object stores. There are no list operations, which is one of the things that caused the most time, especially if you were using tables stored in S3 or some other object store. A list operation can take an incredibly long time. Not to mention, for a long time, they were not consistent. So if you got a list operation back, you didn't know if that was really the set of files there or not. So listing is not a great thing. Even now that S3 has consistent listing, really what you're doing is waiting for all of the nodes to say, yep, I got that list. So it's a trade-off between the latency of other operations and correctness of your list operation. Iceberg also doesn't use any rename operations, which doesn't really affect the performance all that much. Although if you're renaming all the files in a table, it can take an incredibly long time at commit time. but we're not really focused on the actual write time for Iceberg today. What we're focused on is the read path. The only thing I want to say about rename operations is that they're unreliable. So anything that relies on a rename operation in S3 in order to be correct is simply not reliable. So watch out for that. The other thing that I think we're going to talk most about today is Iceberg's metadata tree. And this is sort of the details of how Iceberg is built for object stores. The metadata tree gives us a few really nice properties: faster planning, fewer tasks, and that really comes from we don't have to list anything. We have a small set of files that we can just scan through. That's the faster planning part. And then we're also keeping additional metadata about all of the data files in the data set, and that's how we get fewer tasks. Now, in addition, the metadata tree in Iceberg also helps us keep write amplification low. That's for faster writes, more efficient write operations and things like that. That's not something that we need to really dive into much today, but just know that another property of this tree is being able to keep track of what is changing and rewrite just portions of the tree that are changing. And then the last optimization that we're unfortunately not going to talk about at all today is the addition of delta files. So Iceberg's v2 specification includes delta files that allow you to mark rows deleted in immutable files that make up your data set. And that, again, really reduces write amplification and also makes just general write queries quicker. So we're really looking forward to getting that support into Trino, because the merge into and delete from plans that I think are really on that developer productivity end of the spectrum are going to be super valuable once we can get everything working with the delta files. All right. So we're going to dive into this middle one, the metadata tree, just a little bit more to help everyone understand what I'm talking about here. So Iceberg metadata forms this tree structure that you can see on the right, where you have a manifest list, and that's one-to-one with every version of the table. Every version or snapshot in Iceberg has a manifest list. And you can see how the data is laid out here. A manifest contains multiple data files, and the state of a table is the union of all data files listed in all manifests listed in the manifest list. This is the structure that allows us to have really fast planning times. So for example, we can take the manifest list and go through and figure out which manifest files we actually need to read for any given query. So instead of reading all 3 manifests here, we probably only need to read just 1. Then we can go and read that manifest and push down our filters, pruning by partition. And by the way, Iceberg will convert your row filters into partition filters automatically. So these are actually hidden columns that you don't have to see at all. So if we're partitioning by date of some timestamp, you only have to filter by timestamp. Iceberg will convert that filter into a date filter and correctly select data files. And that's really fast because those values are in the manifests themselves as a tuple of partition values. So that's a really fast way to scan through the manifests. And then we have a secondary filter. This is a bit slower because it uses a lot more data from the manifest, but we're still using metadata at the table level. So what we'll do is we'll load all the column stats and then take the row filter and make sure that the column stats or column ranges overlap what would match that filter to further reduce the number of data files. Then we also push down the filters into the data files themselves. So we support both Parquet and Orc, and we'll skip entire stripes or row groups within those structures. So you can think of Iceberg really as an extension of what you're already familiar with in columnar formats. You're basically keeping extra metadata about larger and larger portions of your data in order to be able to skip those. So we can skip manifests, we can skip data files, we can skip row groups or stripes, and everything is really super fast because of that. So let's get into a little bit more detail with an example. So here, this is the top portion of an Iceberg metadata tree. Over here on the left, we have snapshot 1's manifest list, and that lists manifests. Here we see manifest 1.avro, manifest 2.avro, and some summaries of the partitions that are in those manifests. Though that is how we do the manifest filtering in the first place. Then on the right, we have manifest 1 and manifest 2. And as you can see, we have partition values for each data file, as well as a map of lower and upper bounds. What we're going to focus on first is the ranges of partitions in each manifest. So given our filter, ID equals 74 and timestamp between, looks like October 1st and October 4th, we can go and take a look and see that only manifest 1 matches, because the lower bound of timestamps is October 1st through October 15th, and we know that that matches our query range. The manifest 2 partition summaries show that it's October 15th through October 31st, which I should have updated to October 21st because 31st is in the future. But anyway, we can see that that doesn't overlap our timestamp range, so we don't have to use that at all. Now, we also see that we have a column that is a bucket of IDs. So we have a 64 width bucket function on the ID field. And each manifest looks like it contains all 64 buckets. So we have 0 through 63. So that doesn't help us actually filter out manifests at this point. But we were able to ignore manifest 2 and probably other manifests here. So then we move on to reading just the manifests that we need. And we can see that here, that's when the partition data actually helps. So through our bucket or hash function, 74 turns into bucket number 1. And so I know that I only need to read bucket number 1, or sorry, data files for bucket number 1. And so I can really filter down. I'm eliminating 63 of the 64 files that might be there for every day. So we're only going to read the files for October 1st, October 2nd with bucket ID 1. Next, we're going to push down even further and start looking at the lower bounds and upper bounds of each column of each data file. So this is, again, manifest 1.avro. We were previously going to read file 2 and file 65 because we looked at the partition values. But now we can see the lower bounds and upper bounds of the ID. And here, the data file 2, the ID lower bound is 186. That hashes to partition 1, and we have some range of values. But I can see that ID number 74 is not in that range. So I don't need to read that data file at all. Likewise, I see that with data file 65, the lower bound is 65. 74 may not be in there, but we still need to read the data file. So really quickly, that was a very fast run through of all the filtering Iceberg does at the table metadata level. And that is really how we get very fast job planning. Now, a couple of caveats to this. If you're ordering data across or within files, you can make those file scans even faster. So in our example, the IDs were in basically every data file had the span of IDs. But if we wrote multiple IDs for each bucket, or sorry, multiple data files for each bucket, then we could have a range of, say, 0 to 500,000 and 500,001 to 10,000, a million. And we could further skip data files. And the same thing goes for row group or page level skipping within data files. So clustering your data is going to make scans even faster, and Iceberg is going to be able to take care of or take advantage of that clustering across files. Now, the other thing I want to mention is that sometimes writes don't align with the reads. So if you're, all of this really matters in how your data files are grouped into manifests. If every manifest may contain a data file that matches the query, then we have to read every single manifest. And that's not great. What we do in Iceberg is we keep data files grouped by when they were written. So writes in time that were near one another, those data files are grouped together. That helps because we assume that your write pattern aligns with your read pattern. So imagine if you're writing data through a Flink-like system, all of that is clustered together in time, processing time. And if you're also consuming it by time, saying, oh, I need the data from the last month or the last week, then that aligns really well. And we don't have to do any manifest management. On the other hand, if you were using like a bucket system and you wanted to really quickly look up just certain buckets without a date filter, then you might want to rewrite your manifests to cluster data by bucket rather than by time. And to do that, we have system calls. So stored procedures, I don't know that this is implemented in Trino yet. You might have to use Spark for this, but you can also always go back to the table API, call table rewrite manifests, and recluster the metadata of your table to align with reads. This is one thing that we did to get incredibly fast queries. So those are that's the setup for my results page. So the log data here that I have listed second, we were able to get results in less than 5 seconds on a multi-petabyte data set. This was looking up individual IDs. We just need, all the logs for, say, this device or this machine. There were more than 2 million partitions because we were using, I think, 7 days of data and something like 20,000 buckets, so that we could really quickly zoom in on just the data that we wanted. And we used Trino for this use case. We had to rewrite the metadata in order to cluster everything so that we weren't reading too many manifests and we could keep the job planning time to a minimum. But this would literally not be possible with any other big data system or big data storage format. So this was a really cool result. We were running, basically a dashboard. Someone needs access to logs for this particular machine, and we can get that in 2 to 5 seconds. Okay, and then the other thing I want to mention is, with metadata rewrites aside, we had this metrics data, and this was one of our very early use cases. We were only able to query it for a matter of days because it was a huge data set. When we looked at a query over several days, the job planning time was 12 minutes. This was running, I think, 10 parallel threads, trying to go list directories in S3. It was really terrible. And again, if planning time takes 12 minutes, it doesn't matter that you're running things in parallel, because you've got to make sure that, that is the lower bound for your query runtime. After we converted this table to Iceberg, the total runtime of the system or of the query was reduced to 45 seconds. So 12 minutes planning, who knows how many hours, because we never let the job finish in runtime, reduced to overall 45 seconds. And that was really the power of using the clustering within the data and those statistics that we keep in Iceberg to filter down the data and just not run tasks for files where we know the data can't exist. You can only do that if you keep track of more information. So with that, I want to talk just a little bit about future work. I think that Iceberg and Trino together make a pretty stunning combination, but it's not all perfect yet. So there are still things that we want to do. First of all, there's a slight problem with stats estimation between Iceberg and Trino. So Iceberg wants to give as accurate of stats as possible, by keeping all of the stats information at a file level. So you basically plan a query, use that to figure out your stats. Well, if you're trying to run the query at the same time you're running the if you're running the query at the same time you're planning the query, then you can't finish the plan and then get the stats and then figure out what your query plan is. So we want to improve that stats estimation so that we can get faster stats estimation back to Trino for that plan. Another thing is we want to avoid unnecessary S3 calls. File system makes a lot more calls than Iceberg's weaker file IO abstraction. So file system, for example, cares whether something is a directory because you don't want to create an object that is already an existing directory. Well, Iceberg relaxes that constraint and says, we don't care about directories. So we don't need to list a location before creating an object. Those unnecessary S3 calls are something that we'd really love to get rid of just to further reduce that latency. The last thing, or there are two more, but the last big one is we want to get Trino using table level configuration. So rather than specifying in the connector, I want to write everything as Parquet, we know that there are a lot of things that should be tuned per table. So the compression codec, the Parquet row group size, those sorts of things, putting those in table configuration like we do in Iceberg makes automatic table-specific tuning possible. And we really want to get to the point where Trino is respecting all of those settings. So that's something that we're going to be working on as well as I mentioned the row level deltas. We're going to be adding those. I think there's already a PR out for that though.